Thank you so much for the kind introduction, and thanks to everyone for attending this webinar today. As you can see, the title of our presentation today is Good, Better, Best, Pushing the Limits in Optical Spectroscopy, and this is being brought to you by PerkinElmer. I'm Dr. John Bertels, and I'll be starting off part 1 of the presentation, and then my colleague Doug Townsend will join me and take over for part 2. We will then be taking a few questions at the end as time permits. So we'll start here with the usual outline of material being presented today. I will be initially discussing optical spectroscopy from the UV or ultraviolet visible near-infrared perspective. Then Doug will present some relevant material from the IR infrared end of the spectrum. Digging down a little bit deeper, I'll be defining and highlighting sample compartment options, detector compartment options, and then finally some of the latest developments in the Goniometer-based accessories. And then Doug will be discussing some of the challenges in measuring optical components and ordinate accuracy verification. And just to be clear, the two ranges of instruments highlighted here for the two wavelength regions of interest are usually referred to as the Lambda Series and the Spectrum 3 series. So here we see a familiar representation of the electromagnetic spectrum with the energy increasing from right to left and the corresponding change in wavelength increasing from left to right. If we focus on the UV visible colored region of the spectrum, we can see that the approximate wavelength range of interest for this technique lies between approximately 200 nanometers and 2500 nanometers, though the exact numbers will be defined not by theory, but by limitations in hardware and detector design. The actual working range can certainly be extended beyond these values depending upon what hardware options are available. The corresponding instruments used to probe electronic processes in this range are seen here. In the top left, we see the Lambda 1050 Plus. This is an example of a higher performance instrument. In addition, two fluorescence-based instruments have recently been introduced to complement the Lambda series, seen here in the lower left. The wavelength range for these particular instruments is 200 to 900 nanometers. The Spectrum 3 series of instruments, seen on the right, have been designed to cover a broad wavelength range that covers various application areas such as infrared optics and vibrational analysis of molecular materials. A starting point for this region of interest is traditionally defined to be 4000 to 400 wave numbers, or 2500 nanometers to 25,000 nanometers. Again, technology and hardware design dictate how easy it is to analyze materials beyond these values. Here are some typical examples of spectra generated by these instruments. Since we'll be discussing transmission and reflectance measurements later, I've included an example of each. Reflectance of a first surface gold mirror as a function of incident angle, and a transmission spectrum for a challenging curved but important material, a pair of safety glasses. Examples of infrared spectra include polyethylene terephthalate in absorbance mode and a germanium window in transmittance mode. We can now turn to the current family of instruments and highlight the good, better, best approach as it pertains to the UV-Vis portion of the PerkinElmer portfolio. Good, better, best is a great way to understand the demands of a measurement and how instrument performance helps define that demand when assessing the optical properties of any material. We can split the family of instruments into entry-level, platform, and high performance. This helps us to more easily navigate the instrument landscape. Entry-level instruments include the Lambda XLS and Lambda 265. These are diode array-based instruments that allow the user to scan a broad range of wavelengths simultaneously. These are fine instruments for routine liquid-based analysis as found in a QA/QC lab or a high-throughput routine testing lab. Platform instruments include the Lambda 365 and Lambda 465 for a broader range of sample types and measurement challenges. The 365 is a type of workhorse instrument, whereas the diode array-based 465 is designed for speed. Indeed, the 465 can acquire complete spectra in 20 milliseconds. The current range of high-performance instruments include the Lambda 850 Plus and the Lambda 1050 Plus. In the former case, the wavelength range is limited to 900 nanometers, and in the latter case, the wavelength range can be extended to over 3 microns, depending, as always, on the accessories employed for the measurement. We will speak to these accessories shortly. In addition, as mentioned earlier, there are two fluorescence-based instruments, the FL6500 and FL8500, that expand the portfolio such that material processes that lead to fluorescence or phosphorescence can also now be investigated. Whether a material will exhibit these properties will depend upon whether internal conversion becomes competitive with non-radiative processes such as thermal loss or collisional quenching. So we'll take a quick detour to showcase the fluorescence instruments now. The LS55 and its predecessor, the LS50B, were extremely popular benchtop fluorimeters designed to meet the needs of a broad array of biological, chemical and materials applications. This newest generation builds upon that heritage by incorporating additional design features for enhanced flexibility. The FL6500 is powered by a variable energy pulsed xenon lamp, which is ideal for materials susceptible to photobleaching or photodegradation. In contrast, the FL8500 exploits a bright 150 watt continuous wave xenon arc lamp, which therefore allows for higher sensitivity and thus in turn higher scan speeds. Thus, the 8500 is ideal for smaller samples, solid-state materials, or complex liquid mixtures that sometimes require data-rich 3D spectral scans. We see here one of the accessory options, the 100mm integrating sphere, which can be used to extract quantum yield data for materials via popular protocols such as the absolute de Mello method, first described in 1997. So that was a brief detour into the world of fluorescence. Now we can summarize the aspects of an instrument that make them good, better, or preferably best. This includes choices for the lamp or energy output, the type of wavelength selector used, be they array-based, filter-based, or grating-based. The ability to therefore reject unwanted wavelengths of light, aka stray light, is therefore critical if one wants to measure a high absorbance material such as an optical filter. The choice of detector, be it a silicon photodiode, narrowband InGaAs detector, or PMT for example, is also of fundamental importance. And finally, instrument stability, as required for more demanding measurements. This will be enhanced by employing a double beam ratio recording system as well as a large robust instrument base to minimize thermal drift. So, fundamental optical processes are essentially due to a material's ability to respond to an oscillating electric field, since all materials are composed of electrons, either bound or free, as well as nuclei or ionized atoms. So how does this then translate to the more traditional length scale, the macroscopic lab-based length scale? There are really two variables that we can measure most easily, namely reflection and transmission, and we can therefore also deduct with some care the lack of those processes and label that as absorptance. That is to say that absorptance is equal to 1 minus reflectance minus transmittance. But we can dig deeper by dividing these processes into specular and diffuse. This is a somewhat arbitrary delineation, but it turns out to be extremely useful for defining measurement demands and associated applications. In this context, we loosely define diffuse scatter as any electronic oscillation that leads ultimately to the redirection of light in some other new direction that is measurably different from the original direction. Additional processes shown here are simply manifestations of that same fundamental electron-photon interaction. In the case of molecular materials, we might catalyze a chemical reaction or break a bond, or in the case of those materials in which internal conversion becomes a competitive process, we may observe fluorescence as highlighted earlier. The macroscopic processes defined on the previous slide hint at the measurement challenges encountered in real-world samples. The majority of real-world materials are non-ideal, which leads to some of the scenarios highlighted on this slide. Since sample analysis necessarily requires two measurements, with and without the sample of interest, any scenario where the light path is modified in its interaction with the detector can potentially compromise data accuracy. Furthermore, even the detector itself, seen here on the right, should not be assumed to be homogeneous. Thus, the detector output can also vary as a function of illumination area, which itself will depend upon the sample in a variety of ways, such as angle of incidence or the sample's own internal structure, perhaps by design, for example, a multi-layered mirror or optical filter. So the high-performance Lambda series of instruments have evolved considerably over the last 40 years. The incorporation of components such as multiple diffraction gratings, appropriate light source, and sensitive PMT in-gas detector combinations is a prerequisite for a high-performance instrument. In addition, however, the evolution of the series from instrument to modular platform has been required to accommodate the various measurement challenges that new technologies and materials are now bringing to the table. Indeed, there's an old saying that comes to mind: if we can measure it, then we can make it. To summarize recent progress, we can view the evolution of the Lambda series here, from the Lambda 19 in 1991 to the modular platform of the Lambda 900 in 1996, to the current series, which offers a complete range of accessory-driven measurement solutions. So this shift in emphasis from sample to detector compartment flexibility means that we will focus on this region first before returning back to the sample compartment. The region now flashing is the detector compartment area. The area to the left is the traditional sample compartment area, typically used for liquid-based cuvette measurements as well as many solid-state measurements. More on that later. And we can see now an example of this detector area modularity. The example shows one of the transmission modules being removed such that it can be replaced with an appropriate reflectance-based accessory. In this case, the Universal Reflectance Accessory, also known as the URA. So this brief example has highlighted the fact that modularity is a prerequisite for high performance, in addition to the hardware components that must be deployed appropriately. Please note that the instrument needs to be powered down when you do this. To make this point clearer, we will now navigate briefly through some light schemes to show you how the detector compartment can be easily changed to adapt to any measurement challenge regardless of sample size or shape. So here we see a representation of the 1050 plus standard detector configuration, designed for well-defined optical components. The detector consists of a PMT, InGas and lead sulfide to cover an extended range from about 185 nanometers up to about 3.3 microns. Very briefly, we can also see the dual lamp compartment in the top left, the dual grating system for low stray light levels towards the center, and the chopper assembly which converts the instrument into a more stable dual sample beam reference beam ratio recording system. If we purge the instrument with nitrogen, there are two gas inputs on the top left side. We can also remove a significant amount of the oxygen within the 1050, and in doing so lower the wavelength range to about 175 nanometers. But this is certainly a difficult measurement. Just to clarify further, oxygen will absorb UV energy at around 200 nanometers. In this scheme, we are highlighting the two of the goniometer-based accessories that can sit within the detector area. That is the TAMS, Total Absolute Measurement Accessory, or the ARTA, Automated Reflectance Transmittance Accessory. In both cases, the sample and detector stages can move independently for multiple measurement scenarios. Note that the ARTA actually installs into both the sample and detector compartments, but conceptually the two are very similar. These accessories will be discussed in more detail later. Here we see another key detector accessory, the 100mm integrating sphere. As mentioned earlier, spheres are critical for measuring a whole host of materials that scatter light in such a way that accurate measurements are not possible with a standard PMT detector, sometimes referred to as a direct detector. In this case, we can see the sphere contains a PMT and InGas detector, which is the recommended combination for this detector type, though other options do exist. And then finally, we see here the larger 150mm integrating sphere, sometimes referred to as an absolute sphere, since the data is often considered to be the most accurate, though there are certainly exceptions. The internal sphere material and the preferred detector combination limits the wavelength range of this accessory to about 250 to 2500 nanometers. Going below 250 is certainly possible, but remains challenging due to lack of energy. To conclude this section, we can highlight some, but not all of the integrating sphere design types and sizes that are possible. For example, the sphere shown in the center is a large compartment integrating sphere designed for larger glass samples. Larger glass samples are often standard in industries such as automotive, display, and solar-based technologies. There are some situations where even these spheres are simply not up to the job of integrating scatter in order to generate an accurate output, be it a transmission or reflectance time measurement. Here on the right we can see materials that are designed to enhance the natural lighting of a home or office building and moderate temperature by regulating the flow of light and heat in a controlled way in specific directions. Thus, these materials are often non-isotropic, which makes it very challenging to measure their transmittance and reflectance accurately. On the left, we see that the size of the sample and the size of the beam and even the size of the port itself can have an effect on the final measurement, since we may be sampling the materials differently when we change those variables. On the left, we see the 270mm sphere installed on a high performance Lambda. On the right side, we see the sphere being used in reflectance mode. In fact, this sphere can be used in either transmission or reflectance mode, and there is no need to move the sample when switching between the two. The beam that interrogates the sample is simply diverted either way by virtue of a small mirror that switches back and forth, and this is highlighted in red on the right side. The entrance port can be swapped out if the complexity of the sample dictates that a larger entrance is required to generate a more accurate output due to enhanced scatter from the sample. So now we've looked at deploying integrating spheres and how they can be exploited when sample measurement challenges really push the spectroscopy to the measurement limit. But we can also use some of these spheres in other ways that push optical spectroscopy when performing other types of specular type measurements, not just diffuse. Let's go back to what we refer to as the standard detector configuration from before, but now instead switch our attention to the sample compartment. This is the area to the left of the detector compartment. In many cases, samples and appropriate high-performance accessories can also be installed here to facilitate very accurate measurements. Indeed, in earlier times, when the detector compartment was considered to be passive in its ability to facilitate challenging measurements, all of the difficult measurements were performed here instead. That option still remains to this day, so it should also be considered when performing challenging measurements. In most cases, an integrating sphere will be required within the detector compartment area due to the reasons highlighted earlier. The beam-sample interaction can compromise the necessary comparison between baseline and sample measurements. And here is the actual compartment again, highlighted now in red. And now we have figuratively installed an appropriate sample compartment accessory. These exist in a variety of designs. Some of them are very accurate, but they therefore require extra user care and attention. There is an alphabet list of manual, i.e. non-automated accessories which can be deployed within the sample compartment. These include the VN, IV, and RT accessories, for example, or in this particular case we see the VW accessory, which can be used to generate accurate specular reflectance measurements on well-defined higher reflectance mirrors and optical components at any angle between approximately 8 and 75 degrees. In this initial example, the sample, circled in red, is placed in the center rotation stage, but to perform the measurement we do the following. Remove the sample in order to acquire the baseline or background measurement. In the so-called V mode baseline measurement, the sample beam interacts with three mirrors labeled M1, M2, and M3. Then in the so-called W mode, the sample is carefully inserted such that it interacts twice with the beam via mirror M2, which has now been moved to the location as indicated by the red arrow. Two things should be noted here. First, that this is an absolute method, that is, no other reference material is needed to produce the measurement. Secondly, the two sample bounces mean that we are actually measuring the square of the sample reflectance. Thus we can then calculate the square root of the output to record the true final reflectance value. The IV accessory is conceptually similar, but the incorporation of a beam splitter into the stage design, circled in red, means that the two sample bounces are now registered as being at the same incident angle. This leads to the V designation rather than the earlier W mode. In this example, we can see how acquisition of two theoretically equivalent incident angles, but they actually aren't equivalent, can be recorded. It can be shown that to extract the absolute best data for any sample, a long list of spectral measurements must be recorded. In fact, 24 for both S and P polarization at any incident angle, in order to monitor and calculate the reflectance of specular materials. That is required to isolate linear drift over the time span of the measurement and estimate error contributions such as stray light, detector nonlinearity, systematic deviations in wavelength, incident angle, polarization orientation, and sample non-homogeneity. So we've seen that exploiting the sample compartment in an appropriate way can lead to very accurate measurements, though this requires a lot of time and an end user who is experienced in metrology and or analytical techniques. If we now switch back to the detector compartment area, we can now briefly explore other ways that allow for accurate measurements, but with the added automation, which then allows the end user to move on to other tasks within the lab. So let's remind ourselves of the earlier light scheme that highlights the goniometer-based independent sample and detector stages that allow us to vary both the sample incident angle and the detector collection angle. There are actually several ways to implement this approach. The ARTA was developed around 2000 for the Lambda 900 and then optimized and upgraded around 2007 for the Lambda 950. The sample is inserted into the center of the accessory such that the sample and detector can move independently to generate specular as well as off-angle measurements. The key features of this accessory are the incorporation of an integrating sphere type detector assembly, which is critical for these types of measurements. Furthermore, contained within the sphere are the powerful combination of a PMT and an in-gas detector for the near-infrared to offer unprecedented performance across the entire wavelength range. Lastly, unlike the TAMS, a fiber optic bundle is used to feed the reference beam into the sphere, making this a true double beam integrating sphere. The use of a goniometer type system is instructive since it serves as a reminder of some of the design limitations of commercial spectrophotometers. The sample beam, by virtue of the gratings and the optical path through the instrument, will not be completely homogeneous. This means that there is a need to collect two equivalent angles when trying to collect the most accurate data possible. Furthermore, since the beam is not homogeneous, when we attempt to measure the sample relative to some background measurement shown on the left, the beam would have been flipped by virtue of performing the reflectance measurement itself, and that cannot be avoided. The problem is compounded by the fact that the detector is also itself non-homogeneous, and different detector technologies will respond differently in this situation. The best approach is to employ an integrating sphere as a means of scrambling the reflected beam to remove detector bias. Data shown on the right illustrates the beam bias as seen for transmission data for infrasil glass at +60 and -60 degrees. The sets of data for equivalent angles are not the same, such that two measurements must be made and an average calculated to generate a meaningful value. The total absolute measurement accessory was introduced to supplement the ARTA with a more cost-effective solution for a broader user base. Conceptually, the TAMS is similar to the ARTA, but with some key differences. The TAMS possesses a smaller footprint, exploiting the right-hand side detector area only, and not the combined sample and detector areas, as the ARTA does. The TAMS can measure larger samples due to the large sample breadboard base. This sample base plate therefore offers up additional flexibility for unconventional materials if needed. The control software is also the same for both the TAMS and ARTA and is intuitive to use. As with the TAMS, only one baseline auto zero is required before performing sample analysis for all angles. There is no need to perform multiple measurements beforehand. Most importantly, the TAMS detectors are modular. This gives the end user a choice in how to collect data that is meaningful and sufficiently accurate for them and their analysis needs. The detectors are sandwich-based, consisting of, for example, silicon and in-gas or silicon only. There are actually 7 different TAMS detector options for different materials, different measurement demands, and different wavelength ranges. We will highlight 3 of them shortly. Here is a cutaway view of the TAMS. Unlike the ARTA, the TAMS consists of 2 separate detectors for the sample and reference beams. The reference detector can be seen towards the back. Thus, it is not a true double beam detector-based system. The sample stage shown here shows the default sample holder, typically for glass samples which range in size. However, this stage can also be used for smaller circular samples. Much larger samples can also be accommodated with some minor modifications. Here is an additional cutaway of the sample detector, showing in this case an integrating sphere-based detector. The lower image illustrates how the focusing mirror directs the beam into the sphere. This is critical for slightly curved or thicker samples. Finally, 2 screws are highlighted here. These allow the user to remove the detector. No service engineer required. So we've opened up the discussion to include thoughts on the need for modular detectors. But why won't one detector do everything? As a reminder, here is the early schematic that shows how the baseline measurement and the subsequent sample measurement are always going to be different. The beam itself is not homogeneous. The detector used for both configurations is not sufficiently homogeneous either. So a true comparison between the 2 configurations, which then generates the data we are really interested in, is difficult. And there's another factor. What if we are dealing with a thicker sample, typically glass, for which the additional secondary and tertiary reflections are considered to be a critical part of the measurement process? In the image shown here, there are 4 sets of reflections that could contribute to the final observed reflectance spectra. Without a sphere-based detector, these photons would be missed and the data would be compromised. So this observation then leads to a design of multiple detector sets. Any or all of these detector sets can be used with the TAMS, and they can be switched out in a few minutes. As an example, we split the detector types here into sphere-based and direct, where direct refers to a non-sphere type detector. These direct detectors are inherently more sensitive, but they usually won't possess the accuracy of sphere-based detectors due to the challenges highlighted earlier: imperfect sample, imperfect detector, imperfect sample beam, and thicker samples. Here's an example of the TAMS detector modularity. We can highlight the 3 options for the specific silicon in-gas detector combinations here. This covers the range from 200 to 2500 nanometers. The standard combination is great for many routine measurements, for example, first surface mirrors or thinner glass samples. However, if scatter measurements are of interest, then a larger, more sensitive direct detector, which can also handle thicker samples without the need for an integrating sphere, might be more appropriate. The best option is then shown here. A larger detector within an integrating sphere with 2-stage thermoelectric cooling is the highest performing detector. Thicker samples and very low noise in the near-infrared make this the premium detector option for the TAMS if needed. And reference detectors are shown here on the left. Finally, since automation was mentioned as a way of pushing optical spectroscopy into other application areas, I will briefly highlight the TAMS Autosampler stage. This is the latest of the TAMS options. In this case, the Autosampler stage plugs into a connector which is embedded into the base plate itself. This is normally hidden beneath the default sample holder. There are 2 Autosampler holder options for either 5-witness samples or, as seen on this slide, 19 1-inch samples. Thus, 19 samples can be interrogated in multiple locations and at any incident angle, and that is a lot of data. Finally, since the autosampler needs to move vertically to reach each position, the TAMS lid has to be swapped out to the taller version shown here in order to accommodate the accessory. Easily done in minutes or less. And with that brief overview of the Lambda series, I'll now hand over the reins to my colleague Doug, who will be discussing the Spectrum 3 series of instruments.
All right, thanks, John. In the first section of FTIR, we will very briefly discuss navigating the instrument landscape with a focus on the Spectrum 3 FTIR from PerkinElmer. Next, we will discuss the Spectrum 3 Optica and how to verify its performance for measuring samples that require extremely high ordinate accuracy. When it comes to the good, better, and best approaches to FTIR, we can distill the instrument landscape down to performance requirements of the measurement and the sample complexity. Our entry-level Spectrum 2 is an easy-to-use, powerful, and compact instrument that comes in either mid-infrared or near-infrared wavelength ranges, with a flexible range of sampling accessories and detector options to help laboratories balance performance with cost. The conservative design of the Spectrum 2 makes it a great choice for routine sampling such as raw material identification and quantitative analysis. For research-grade performance, the Spectrum 3 enables a busy analytical or research laboratory access to the broadest scope of applications. The system combines optimum performance in the mid-infrared, near-infrared, and long wavelength regions with extensive sampling versatility, all in a single instrument. For even more challenging samples, both the Spectrum 2 and the Spectrum 3 can be coupled to our Spotlight series FTIR microscopes. Sometimes a single instrument or technique doesn't yield the depth of information or insight that you need. So researchers turn to hyphenation, which allows you to acquire valuable information from a single instrument or a single measurement. PerkinElmer's single vendor solution for hyphenation greatly simplifies the experience and reduces the need for extensive training and support. Both platform FTIRs can be coupled with our thermogravimetric analyzers. More recently, PerkinElmer released the EGA 4000, which is the world's first in-compartment TGA accessory, bringing together a thermogravimetric analysis system and the Spectrum 3 FTIR to deliver the simplest and most high-performance system available for evolved gas analysis. A little more information regarding the flexibility of the Spectrum 3 instruments. There's quite a variety of options for you to choose from. Testing all infrared ranges in one lab has always been an expensive and sometimes two-system proposition, and that's the very need that the Spectrum 3 was designed to address. You can choose from single, dual, and tri-range systems to meet your needs without manual reconfigurations. The extended range near-infrared, mid-infrared system uses one beam splitter, one source, and one detector, allowing you to scan continuously from 11,000 wave number to 375 wave number, allowing for an affordable and consolidated dual-range system. For a true dual-range, two-source, two-beam splitter, and two-detector solution, the scan range is larger and you have more flexibility in other detectors such as MCT for the mid-infrared. Finally, tri-range systems cover from 11,000 to 30 wave number for the truly brave souls out there performing far infrared. A wide array of accessories gives you total flexibility to analyze nearly any sample type, solid, liquid, gels, even gas phase sampling. An exceptional signal-to-noise and photometric performance assure optimal spectral performance to ensure best-in-class sensitivity. As part of the Spectrum 3 platform instruments, we have our Spectrum 3 Optica FTIR, which has been designed specifically to address the challenges in achieving high ordinate accuracy on Fourier Transform instruments. The remainder of our discussion will focus on the design benefits which allow the Spectrum 3 Optica to overcome errors that decrease ordinate accuracy. Verification of the FTIR presents a challenge as there is no standard test for FTIR ordinate accuracy in the mid-infrared. Methods to verify instrument performance will be shown by comparing values with transmittance calculated from refractive index values and by comparison to values obtained by NIST. Measurements of optical components are some of the most challenging that can be made with an infrared spectrometer. Typical measurements can involve checking the purity of substrates, measuring the transmittance of designed filters, as well as their ability to block or reflect radiation. These samples have demanding specifications and require the highest level of ordinate accuracy. Since optical sensing systems can contain over 100 components, individual measurements require high accuracy to minimize cumulative errors. A small loss of less than 1% efficiency at each component would make the entire system unable to perform as required. Therefore, an instrument is required to reliably measure a variety of properties in a single run. Whereas most FTIR applications are based on peak measurements relative to a baseline, performance of optical components is specified in terms of absolutes, reflectance, and transmittance. Accurate measurements of these is critical to achieving and maintaining product specifications. As FTIR spectrometers are single beam instruments, ordinate accuracy is more difficult to achieve due to changes in the baseline and other problems such as spectral artifacts and inaccurate transmittance values for such samples. This presents a major challenge for suppliers of optical components because the question inevitably becomes, how do you validate FTIR performance? In fact, over 50 problems have been reported in making accurate ordinate measurements by FTIR. Common sources of error are primarily due to the optical path arising from spurious reflections involving the source, interferometer, sample, windows, and the detector. The nature of the sample can also distort the beam at the detector position, leading to inaccurate results. Furthermore, because all wavelengths are measured together in an FT system, the dynamic range of the interferogram is a potential problem and can lead to electronic sources of error. Completely filling the A to D converter is important to avoid digitization errors. If very high photometric accuracy is required, then it is necessary to think about how the sample interacts with the light from the instrument. The nature of the samples can significantly distort the beam, making these measurements difficult. For example, optically fixed samples can defocus the beam on the detector, while samples with non-parallel surfaces can deflect the beam off the detector. Highly reflecting samples may need to be moderately angled to further deflect unwanted reflections. For years, the PerkinElmer Model 983 Dispersive IR has been the gold standard for the optics industry. Some laboratories are still running the 983, which is a testament to this instrument's value. However, it was last manufactured in the late 1980s, and it was the last of the double mean ratio recording instruments. Despite the universal adoption of FTIR spectrometers for other applications, early attempts to replace the 983 in this industry failed due to errors associated with measuring optical filters on Fourier Transform instruments. While the 983 went away, the need for obtaining reliable and accurate results remained. For these reasons, an FTIR instrument with specific modifications was made to overcome the challenges presented by measuring optical components on FT systems. This was first addressed with the Spectrum GX Fourier Transform infrared spectrometer series by PerkinElmer, which included several design modifications that enabled greater accuracy in measuring optical components. For example, this is a spectrum of long-pass filter required on an unmodified FTIR spectrometer. When interreflections involve the interferometer, double modulation can occur, leading to artifacts outside of the passband. The main problem is the reflection between the sample and the interferometer. In this example, the passband begins around 1500 wave number. However, if we zoom into the blocking region, we can see that there is apparent structure below 3000 wave number at about 1% transmittance. But most of this is actually due to the spectrometer rather than the sample. This can be demonstrated by measuring the sample in the presence of a sapphire window, which is opaque below 1600 wave number, effectively blocking the passband and eliminating these reflections. Intercepting these reflections with masking can allow for measurement of the blocking region, but does not solve the inherent problem. A better approach would be to design a spectrometer capable of eliminating these effects of these interreflections. When measuring this particular sample with the Spectrum GX Optica, these artifacts are eliminated. This is due to the addition of baffles and beam blocks, which again intercept the remodulated light and eliminate these artifacts. Another example is shown here in the transmitting region of a germanium window. The erroneously high transmittance is due to the aforementioned interreflections between the sample and the interferometer. Here the inaccuracies can be greater than 1%. In the Spectrum GX Optica, the errors due to interreflections was addressed, shown here in the blue spectrum of germanium, which is devoid of these artifacts. The spectrum shown here is that of a high-performance narrow bandpass filter collected on a GX Optica. The transmission at 1596 is around 4000 wave number for the passband. When inspecting the blocking region, two artifacts appear around 3192 and 4788 wave number, which correspond to integer multiples of the original passband frequency. These features vanish when the region below 2000 wave number is blocked using a glass slide, demonstrating that these features are not genuine and instead arise due to spectrometer errors. These are likely optical errors due to remodulation, since blocking the passband eliminated these artifacts. This example demonstrates that any residual artifacts appeared at or below the level of 0.01% transmittance in the modified spectrum GX Optica. So we've shown that errors in spectrometer design and other artifacts exist in unmodified spectrometers and even persisted for challenging samples on the GX Optica. PerkinElmer recognizes these errors and continues to integrate newer and better technology to our spectrometers. The introduction of the Spectrum 3 Optica, formerly known as the Frontier Optica, solved many of these outstanding issues in achieving accurate transmittance measurements and further eliminated artifacts due to electronic errors as technology progressed. The Spectrum 3 Optica has been designed to allow the operator to better optimize the instrumental parameters for a particular requirement by delivering an extra degree of control over both the beam size and the divergence at the sample position. The Spectrum 3 Optica has been designed to eliminate interreflections involving the source, interferometer, sample, windows, and detector. There are baffles to block interreflections between the interferometer, the sample, and the source. All windows and the detector are angled to further deflect reflections. To minimize the consequences of beam distortions by optically thick or wedged samples, the Optica has two variable apertures in the beam. These provide independent control of the size and the divergence of the beam. The use of delta sigma analog to digital conversion avoids the need for gain switching and ensures excellent linearity. With regards to the detector, although the linearity of DTGS detectors is widely thought to be well established, the presence of a sample actually changes the detector temperature, with a consequent change in its responsivity. This was identified by the National Institute of Standards and Technology as a major source of error in FTIR measurements of transmittance. And for that reason, lithium tantalate is used as the standard detector in the Optica. One of the key design features is the incorporation of two variable apertures, which allow for increased control over beam size and divergence to accommodate wedged and thick samples. The first is the variable J-stop. Shown here on the right, the J-stop is a variable half-moon aperture, the half-moon to prevent back reflections, and defines the beam size at the sample and on the detector. If the beam is deviated by the sample, there's a chance that the beam or part of the beam could miss the detector. Diameter of the beam at the sample position will be about 1.2 times the diameter of the J-stop. Reducing the J-stop will make the image in the detector smaller, and again reduce the chance of that beam falling off the detector in transmittance mode. Assuming a well-aligned system, if this effect is happening, reducing the J-stop will probably increase the apparent transmission, which would be good. The second variable aperture is the B-stop, which is a circular aperture that defines the area of the beam passing through the interferometer. It also controls the divergence of the beam at the sample position by restricting the angle of the cone of radiation, which further reduces the divergence of rays reaching the detector. On the right, you will see a filter wheel looking down the axis of the beam. The magenta circle is the B-stop, which controls the size of the beam passing through. In general, for a thin window-like material and percent transmittance, approximately normal to the beam, closing the B-stop will reduce the divergence of rays passing through the J-stop image at the sample position, thereby producing a more collimated beam. This will reduce the chance of the beam missing the detector or some of it falling off the detector. If this is happening, you'll actually see erroneously low transmittance, assuming no back reflection and double modulation artifacts are present. If this effect is taking place for a large B-stop, reducing the size of it will probably increase the apparent transmittance and thereby increasing the accuracy or the correctness of the measurement. Together, these two variable apertures work together to facilitate control over the beam size and divergence through the optical path. For example, a given measurement of a relatively thick optical filter might be concerned with absolute bandpass accuracy. Here, minimal beam divergence at the sample is preferred. Alternatively, another sample might require low noise or low artifact measurement in the blocking regions, where a higher beam divergence would deliver lower noise results more quickly. The Spectrum 3 Optica provides additional flexibility to optimize the measurement conditions to suit the application requirement. This brings us back to our original question. How do we verify the performance of FTIRs? Verification presents a challenge because there is no standard test for FTIR ordinate accuracy. Recognized tests exist for dispersive infrared, but these may not be adequate for real sample situations. However, there are two alternative methods available to us. One is to rely on transmittance calculated from refractive index values that are often known to very high accuracy. The other is to use traceable reference standards from suppliers such as NIST or NPL, but such standards are not currently available for us in the mid-infrared region. We've taken both approaches at PerkinElmer using germanium windows that have confirmed the transmittance values by having the samples measured at NIST. In the first approach, we measured a 1 mm thick germanium samples on the Spectrum 3 Optica and had the same samples measured at NIST. Measurements at NIST are essentially identical with those on the Optica, the differences being less than 0.1% transmittance over the 5,000 to 900 wave number region, or 2 to 11 microns. The overlap between the two measurements is shown on the left, while the difference between the spectra is shown on the right. In the absence of standard samples with known transmittance values, it has been common practice to compare values for the same sample on different instruments. Shown here is 5 scans from 3 different Spectrum 3 Opticas. When we have tried this with the Optica, the agreement typically tends to be better than plus minus 0.1% transmittance outside of regions of atmospheric absorption. This demonstrates the incredibly high repeatability of this instrument. When it comes to optically thick samples, where their faces may not be parallel, tend to deflect the beam and can give incorrect transmittance values. In the Optica, we have addressed this problem through the combination of a conservative design and optical alignment. Each spectrometer is factory tested using a wedged germanium sample in different orientations to ensure optical alignment. Typical results for a sample with a 0.1 degree wedge are shown here. Another known problem is optically thick samples can change the focusing of the beam at the detector, with the potential of reducing the apparent transmittance. In the Optica, this effect is controlled by the use of the variable apertures to limit the convergence of the beam at the sample. By reducing the J stop and the B stop diameters, we make the beam more collimated and reduce the divergent rays from reaching the detector. The trade-off for this is lower signal throughput, which can be addressed by lower spectral resolution scans or higher averaging while maintaining high ordinate accuracy. This has been tested using germanium windows varying in thickness from 1 to 4 and 6.25 millimeters thick. For these thicknesses, the differences in transmittance tend to be less than 0.2% T above 1000 wave numbers, or 10 microns, where absorption is negligible. To test the performance at other transmittance values than germanium, we have measured zinc selenide, typically 70% transmittance, and calcium fluoride, or 94% transmittance, and compare these results with the calculations from refractive indices, which is our second approach to verifying spectrometer performance. Shown here is zinc selenide measured on 4 separate instruments, demonstrating the high precision of these spectrum 3 Optica. The different spectrum between measured zinc selenide and the calculated spectrum based on the refractive index is shown on the right, demonstrating excellent agreement with differences generally plus minus 0.1% T in regions where absorption is negligible. The ordinate accuracy specification range for the spectrum 3 Optica is 5000 wave number to 900 wave number, but regions beyond that are also showing very strong agreement with calculated values. In both cases, the agreement between the measured and the calculated transmittance is within plus minus 0.1% T in the regions where absorption is negligible. Similarly, for higher transmitting material, calcium fluoride, we observe the same similar agreement, well within the ordinate accuracy specification of the system. If you recall, in a previous example of the spectrum GX Optica, we observed artifacts in the blocking region leading to apparent transmission. This was the result of remodulation of the passband. The elimination of retroreflections or remodulation as a result of design modifications combined with superior electronic processing of the interferogram greatly improves the accuracy in the measurement of blocking regions on the spectrum 3 Optica. The freedom from artifacts means that measurements on blocking filters are limited only by resolution and the noise level. A recommended test for FTIR spectrometers is to measure totally absorbing bands in a film of polyethylene terephthalate. At 4 wave number resolution, spectral resolution that is, these strong bands can be seen to have transmittance below 0.01% transmittance, or 4 absorbance values. This can be contrasted with dispersive infrared spectrometers, such as the PerkinElmer 983, where stray light is typically around 0.1% transmittance. In the absence of standards for FTIR ordinate accuracy, we've taken 2 approaches, comparing data measured at NIST and those calculated by refractive index values. Both have been shown to be in excellent agreement with the spectrum 3 Optica, while eliminating previous sources of electronic errors and optical artifacts. The spectrum 3 Optica is the only FTIR developed for optical filter measurements and the only FTIR with guaranteed ordinate accuracy specifications based on a NIST traceable reference standard. The spectrometer builds on PerkinElmer's experience of providing high-performance instruments for optical filter manufacturers, which we continue to develop and advance. Regarding the 983, which many labs are still using, a word of caution is needed for direct comparisons. There are some fundamental differences between FTIR and dispersive instruments that will affect percent transmittance values for some samples. The optics, the beam geometry, among many other aspects are very different between these instruments. For example, we've demonstrated that the Optica does not suffer greatly from stray light and that limits are set on the resolution and noise, typically about 0.01% T in the blocking region for the Optica, whereas stray light is a more significant source of error with dispersive instruments. Some other differences include the source of the artifacts, where they occur, along with the resolution differences resulting from the inherent differences in the optical designs between dispersive and Fourier Transform instruments. Now, you may have noticed that the spectral range of the spectrum 3 Optica extends well outside of the traditional mid-infrared region and overlaps with the PerkinElmer Lambda 1050 UV-Vis-NIR, which John talked about previously. The accuracy specification is quoted for a range up to 5000 wave number, or 2 microns. Spectra can be measured to 7800 wave number, but there's a significant increase in the noise at shorter wavelengths because of the low source output. However, agreement between the 1050 and the Optica are fairly well within the ordinate accuracy region, typically around 0.1% plus or minus for germanium. As the 1050 is the established standard for optical measurements in the near infrared, and so can be used to verify the performance of the Optica in this region. PerkinElmer remains committed to addressing the needs of high-performance optical measurements as technology progresses. For FTIR, newer models and better technology have revealed further insights to previous designs and their limitations, and we're excited about what the future will bring. Both the Spectrum 3 Optica and the Lambda 1050 represent the highest performance instruments in their class for a wide variety of demanding applications and measurements. The modularity of both systems allows users to expand their measurement flexibility without sacrificing performance. And with that, we thank you for attending, and we'll open this up now to Q&A.